Welcome to this explainer. Have you ever actually stopped and wondered what dictates the delicate balance of life on our planet? Well, today we're decoding the architectural principles of population growth and dynamics. We're going to be translating the wild, unpredictable natural world into the really elegant math that governs exactly how species survive, thrive, and occasionally push the absolute boundaries of their environments.
Okay, let's dive into this with a deceptively simple question. Can any population grow forever? Like, if left completely unchecked, could a single species of bacteria, rabbits, or even us humans just expand into infinity? I want you to keep that in the back of your mind as we unpack these models today.
All right, moving right along to Section 1, the basic math of life and understanding the ebb and flow of populations. So here, we're shifting our focus away from just the individual organism to the collective as a whole. This is population dynamics. It's the study of how population size and density fluctuate over time, driven by things like environmental influences, food availability, and of course, predation. Because biological numbers are never just static. They are constantly moving. And density, well, that acts as nature's vital pulse check. It's an immediate, real-time indicator of whether a species is truly thriving or if it's really struggling. Now, when you strip away all that intense ecological complexity, every single population shift out there boils down to just four basic forces. You've got natality, which is just births, mortality, or deaths, emigration, meaning arrivals, and emigration, the departures. Honestly, that's it. Every rise and fall in a species' numbers is just this continuous, never-ending tug-of-war between these four variables.
Mathematically speaking, it looks exactly like this. N at time t plus 1 equals N at time t plus the sum of births and immigration minus deaths and immigration. I know equations can seem a bit dry, but just think of N as your starting biological ledger. It's the exact population size right at this very moment in time. When you break it down like a bank account, it's actually brilliantly intuitive. Over on the left side, you have your biological deposits, so your new births and arrivals. Then on the right side, you've got your withdrawals, the deaths and departures. It's simple. If your deposits outpace your withdrawals, your overall population account grows. Nature's accounting is really that ruthless, and that's straightforward.
Which brings us to Section 2, the exponential explosion, or what we like to call the illusion of infinite resources.
But what happens when those deposits just never stop? When resources are completely 100% abundant? We're talking unlimited food, perfect space, zero predators, the whole shebang? Well, that is when we hit the exponential growth formula. dn over dt equals rn. Now that little r right there, that is the absolute star of the show. It stands for the intrinsic rate of natural increase. Basically, it is the terrifying maximum potential for a species to reproduce when absolutely nothing is holding it back. To really visualize the raw power of R, let's think about that famous old chessboard anecdote. You place 1 grain of wheat on the first square, 2 on the second, 4 on the third, and you just keep continuously doubling it. At first, it starts off deceptively slow, right? You literally just have a tiny handful of grain by the end of the first row.
But you keep doubling it, and by the 64th square, you don't just have a big pile of wheat. You have over 18 quintillion grains. No way around it, that is an overwhelmingly massive number. And it mathematically proves just how rapidly a single biological population could engulf the entire planet if it was left completely to its own devices.
All right, let's slow things down a bit and step into Section 3, the reality of limits. This is the immovable object of nature. Now, what's really interesting about this slide is the stark juxtaposition between theory and reality. Obviously, we can look outside and see that we aren't currently engulfed by a single runaway species. So on one side, you have that illusion of unlimited exponential growth shooting straight up like a rocket. But on the other side, you have logistic growth, because in the real world, resources are finite. Real-world growth actually follows this S-shaped sigmoidal curve. It definitely starts off fast, but inevitably it hits a wall.
And that wall? Well, that wall is what we call carrying capacity, which is represented by the letter K. You can think of K as the ultimate biological ceiling. It's the absolute maximum population size that a specific environment can sustainably support. Eventually, space runs out, food gets scarce, and this fierce competition just takes over. Basically, K is nature's way of slamming on the brakes.
So, to account for this reality, scientists modified our earlier equation into the logistic growth formula. Notice that extra little fractional piece tacked onto the end there? That is literally mathematical friction. As the actual population n creeps closer and closer to that carrying capacity, k, that specific fraction shrinks. It keeps shrinking until population growth effectively just drops to zero. It's a brilliant way to perfectly model how wild populations truly behave.
Wrapping things up with Section 4, why population dynamics matter, and how we actually apply this math to humanity. Because here's the thing, this isn't just some theoretical biology exercise. This is absolutely vital for our own survival. By charting out actual historical records, like taking a look at a full century of India's census data, tracing those massive discernible growth trends from the 1920s straight through to the 2020s, scientists can actually identify exactly which mathematical curve our own rising human numbers are riding. It's completely crucial because it helps us anticipate how we are going to respond to the limits of our own environment.
Which brings us right back full circle to our ultimate question. We've seen the explosive math, right? And we know for a fact that nature always enforces its limits. So, what exactly is humanity's carrying capacity? What is our K? As we look ahead to the future limits of our own global population, that is the lingering, provocative equation I want to leave you to solve today. Thanks so much for tuning into this explainer.